When a giant star dies, the universe remembers. For a brief and terrible moment, creation runs backward. Light blossoms outward, then shatters. Elements forged in its core are thrown into the void. A billion-year story ends in a heartbeat of destruction. A supernova is not just an explosion, it is a transformation. A wave of light so bright it can outshine a galaxy. A storm of matter so violent it bends the fabric of space itself. It is nature's most spectacular form of farewell. The death cry of something that was once alive with fire. But this is not the story of the explosion. This is the story of what's left behind. The quiet after the chaos, the stillness that follows the storm. In the aftermath of a supernova, the star's outer layers are flung into space, a growing, glowing cloud of calcium, carbon, and iron. These elements drift for eons, seeding new stars, new planets, new chances for life. But at the center, something strange remains. Something so small it could fit inside a city, yet so dense it could outweigh the Sunday. This is no ghost, it is a heart. When a massive star exhausts its fuel, it loses the delicate balance that held it up for millions of years. Fusion stops, but gravity does not. The invisible hand that had once been balanced by pressure now becomes a fist. The star implodes, its core collapses inward faster than thought, faster than light can escape. Electrons are forced into protons, fusing to form neutrons and neutrinos. For an instant, the universe holds its breath, then a shockwave, a blinding light, and silence. What's left is called a neutron star, a sphere only 12 kilometers wide, containing more mass than our Sunday. Imagine taking all the skyscrapers of Earth, crushing them into the size of a sugar cube, and still having room to spare. Imagine a teaspoon of this matter weighing 1 billion tons. This is not poetry. This is arithmetic. The numbers alone feel like fiction. A gravitational pull 100 billion times stronger than Earth's. Temperatures in the millions. A crust so rigid it could hold a mountain that weighs more than Everest, yet rises only a few centimeters high. On its surface, the concept of solidity breaks down. Steel would liquefy, diamond would crumble. The electromagnetic bonds that define matter on Earth are meaningless here, overpowered by the strong nuclear force, the most intense known to physics. If you could stand on a neutron star, your feet would sink through the crust faster than you could blink. The atoms in your body would collapse into a soup of neutrons. Even light, that most faithful of travelers, would curve back toward the surface, trapped by gravity's grasp. And yet, there is order, an eerie calm, carved from unimaginable pressure, a structure born from collapse. To understand what you're looking at, you must first forget what you know about matter. Atoms, as we know them, do not survive here. The immense gravity strips electrons from their orbits, forcing them to merge with protons and form neutrons. What remains is a sea of nearly pure neutrons, tiny neutral particles packed so tightly that they lose their individuality. The star is now a layered monument to pressure. On the outside, a thin crust of neutron-rich nuclei, surrounded by a mist of electrons, a crystalline shell that behaves like a solid, yet carries the density of an atomic nucleus. Beneath that crust, a strange transition zone, where the familiar order of matter begins to dissolve. Deeper still, a superfluid ocean of neutrons, where friction ceases to exist, where rotation itself becomes quantum. And at the core, perhaps something stranger still, a soup of quarks and gluons, the primal ingredients of matter, liberated from the neutrons that once caged them. This is not a world in any sense we understand. It is the most extreme state of matter the universe allows before the laws of physics collapse entirely. From a distance, a neutron star might look deceptively simple. A glowing sphere, faint and small, fading slowly into darkness. But to approach it even in thought, is to feel the full weight of the cosmos compressed into silence. And it is not truly silent. The neutron star speaks in rhythm. In 1967, a graduate student named Jocelyn Bell noticed something peculiar: a radio signal pulsing once every 1.33 seconds. Too regular to be natural, too steady to be random. At first, she jokes that it might be a message from aliens, but what she had discovered was far more astonishing: the heartbeat of a dying star. These pulsars, as they came to be known, are neutron stars spinning at incredible speeds, sometimes hundreds of times per second. Their magnetic fields, billions of times stronger than Earth's, funnel charged particles into beams that sweep through space like cosmic lighthouses. Each flash that reaches us is the rotation of an object, no bigger than a city but heavier than the Sunday. A pulsar does not flicker by chance, it ticks with machine precision. Some are so regular that we use them to measure time itself, rivaling atomic clocks in stability. Even in death, a star becomes an instrument of order. The pulsar's beam is not light as we know it. It is radiation sculpted by gravity and magnetism, twisted by the curvature of space-time. The beams move in perfect rhythm, slicing through the void with mathematical grace. Each one is a message that says, "I am still here." To the naked eye, there is nothing to see, just a point of darkness where a sun once lived. But in radio waves, in X-rays, in gamma rays, the star sings. It is the sound of endurance, recorded in photons. If you could drift above this surface, not stand, but hover in thought, you would see an environment that defies poetry. The ground beneath you is not soil, but a sea of frozen nuclei. Each grain of dust is a mountain of pressure. The horizon curves sharply, wrapping around itself. Space is so curved that if you walked a few kilometers, you would end up where you started. The air above glows faintly from residual heat, but it is no true atmosphere. It is a storm of electrons, a plasma halo governed by magnetism so intense it can tear apart atoms before they fall. This is what remains when fusion fails. Not emptiness, but a different kind of order. The same forces that once tore the star apart now bind it into perfect symmetry. And yet, the neutron star is fragile in its own way. Its crust, though unimaginably strong, is not eternal. As the star spins, as its magnetic field evolves, stressors build up beneath the surface. Occasionally, those stressors snap a starquake, a shudder through an object denser than an atomic nucleus. When it happens, the energy released can outshine the sun for an instant. The star adjusts, corrects, continues spinning, a perfect clock resetting itself. Every neutron star carries the memory of its past life. It remembers the fusion that built it, the explosion that birthed it, the gravity that shaped it. Its very existence is a ledger of transformation: hydrogen to helium, helium to iron, iron to collapse, collapse to endurance. It is, in every sense, a heart, not metaphorically but structurally, a heart compressed until it becomes geometry, a heart that no longer beats with blood but with time. And there is something deeply human in that, to collapse under weight and yet to endure, to lose everything, brightness, warmth, form, and still persist in rhythm, to become smaller, denser, quieter, but not gone. The neutron star teaches that destruction is not the end of meaning. It is its condensation. So, when we look up at the night sky and see the faint shimmer of a supernova remnant, we are not witnessing death. We are seeing a story that changed tense from the language of light to the language of gravity. Somewhere, inside that fading glow, a heart still spins, steady as truth. The universe, it seems, loves paradoxes. The same gravity that destroys stars also creates the most stable objects we know. The same explosion that scatters worlds also forges the material of planets and people. From the violence of collapse comes the quiet of permanence. From the chaos of energy, the architecture of matter. To gaze upon a neutron star, even through the lens of imagination, is to confront the boundary between knowing and wonder. It is to see how the universe writes poetry in equations and builds cathedrals out of density. The fire is gone, the light is silent, but the heartbeat remains a pulse of gravity and time, echoing across the dark. And that is where our journey begins. Not in the noise of creation, but in the stillness of what survives it. In the silence that follows creation, there is a place where matter forgets how to be ordinary, where atoms, once proud and spacious, collapse into intimacy, where a star's memory is pressed flat until it becomes something solid enough to stand upon, if anything could stand there at all. This is where our journey begins, the surface of a neutron star. A frontier so thin, it could be mistaken for a boundary between existence and nothingness. Imagine drifting through the ruins of a supernova, the cosmic dust still glowing faintly from the fire that gave it birth. You pass through curtains of iron, through clouds of calcium, through the smoke of a star's last breath. Then, suddenly, the light ahead sharpens into a single point. A sphere smaller than your city, yet heavy enough to pull the wind from your lungs if you had lungs left to feel it. That point is the remnant, the star's compressed soul. And as you draw closer, light begins to bend around it, curving like water around a stone. The sky itself seems to fold. The first thing you see is not color, but texture. A skin of crystalline matter, smoother than diamond, harder than any metal known to humankind. It glows, faintly blue-white, like moonlight, trapped in steel. To the eye, it looks peaceful, the calm of a frozen lake. But that calm is an illusion. Beneath it, forces rage like tides under glass. The surface of a neutron star is no thicker than a few meters, yet it holds the weight of worlds. The pressure there is 10 trillion times greater than the deepest core of Earth. Gravity binds every atom so tightly that even the concept of ground begins to lose meaning. If you could lower your hand, assuming you still possess one, the atoms in your fingertips would be ripped apart before they touch the surface. The electrons would be crushed into the nuclei. The nuclei would merge into something new. In less than a millimeter, matter would forget its old structure and become degenerate, a fluid of neutrons and protons jammed shoulder to shoulder in perfect silence. There is no air, no breeze, no scent of life, only the absolute stillness of pressure. Time itself seems reluctant to move, and yet there is light. Not sunlight, but something purer, a residual glow, the after-image of birth. The surface still shines with the heat of the supernova that made it, tens of millions of degrees, radiating X-rays instead of warmth. To the universe, it hums like a cooling ember. At this frontier between matter and energy, physics behaves like poetry. The magnetic field lines twist above the crust, billions of times stronger than Earth's, pulling invisible rivers of plasma into arcs that can span entire continents. These lines are not gentle, they crackle, they twist, they hum with trapped lightning. Yet from afar they form perfect order, like silk threads aligning in a cosmic loom. This magnetic lattice defines everything. It shapes the light that escapes, it sculpts the radiation, it locks the star's spin into precision. Each neutron star becomes a tiny clock in the sky, not because of machinery, but because of symmetry. On this surface, you find paradoxes everywhere. It is the hardest known material, yet also the thinnest. It is cold to human senses, yet radiates energy beyond comprehension. It is dead, yet beats with the rhythm of life's first principles: order, pressure, persistence. The crust beneath you is built from nuclei, so neutron-rich that they cannot exist anywhere else in the cosmos. On Earth, such matter would decay in a fraction of a second. Here, it endures for eternity. The structure resembles a lattice ions, suspended in a sea of free electrons. It behaves almost like a metal, though it is far beyond any metal's imagination. Every few meters deeper, the environment transforms. The atomic lattice buckles, the nuclei merge, and the familiar architecture of matter begins to dissolve. But we are not diving yet. We linger here, at the skin where light first meets density. Some neutron stars are calm, others are restless. Those with magnetic fields 1,000 trillion times stronger than Earth's magnetars wear their surfaces like scars. The crust strains under the weight of the field lines, twisting through it. Sometimes it snaps. When it does, the energy released is colossal, a flare that can light up half a galaxy. Yet even this violence comes from beneath the surface, where the calm face hides a storm. From space, such a star might seem serene, a faint blue jewel turning slowly in the dark. But if you could listen beyond sound, you would hear tension. The crust whispers. It creaks under magnetic stress. It hums under rotational drag. The whole star is in conversation with its own gravity. You might ask, how can something so extreme appear so still? The answer lies in balance. Every particle here is caught between two vast forces, gravity pulling inward and quantum pressure pushing outward. They cancel each other so perfectly that the star neither expands nor collapses. It simply is. That equilibrium is fragile, a fraction of a percent change. In the internal equation of state, the microscopic laws of how nuclear matter behaves could mean the difference between a neutron star and a black hole. This surface, then, is not just a boundary in space, but impossibility. Cross it, and even the concept of matter as we know it ceases to apply. If you could somehow float above this skin, you would see the landscape curve beneath you, not gradually, but sharply, wrapping around itself within kilometers. The horizon rises faster than the eye expects. Every direction leads down. The curvature of space-time is visible here, not as a theory but as a geometry you can almost touch. The light escaping from the surface bends backward, struggling to climb free of the gravity well. Photons lose energy, their wavelengths stretching until even color surrenders to red. To distant telescopes, the star's glow is faint, its true heat hidden behind gravitational fatigue, and yet it continues to shine. Even 1,000,000 years after its birth, it glows with a cold fire, not burning but remembering. Sometimes, a neutron star turns itself into a beacon. Its magnetic field is not aligned with its axis of rotation. So as it spins, beams of radiation sweep through space, tracing circles of light across the void. To a distant observer, each rotation becomes a pulse, a heartbeat measured in seconds, milliseconds, or less. These are pulsars, the lighthouses of the cosmos. Their rhythm is so precise that astronomers use them to test the very structure of spacetime. The delay of each pulse, the shift in its frequency, even the subtle wobble caused by a passing planet, all of it becomes data. The star, in silence, becomes a mathematician. Imagine lying beneath such a sky. Every few seconds, a beam passes over you, not bright enough to blind, but powerful enough to alter the atoms in your body. Each flash is a whisper. I am still here. I am still spinning. The surface trembles with that rhythm. When the beam passes, charged particles rush through magnetic funnels, colliding, cascading, releasing light. The crust beneath responds, flexing slightly, transferring tension deeper within. Even silence here has structure. The neutron star is not static. It cools, it spins down, it changes. Its crust thickens and cracks, its magnetism evolves, its heartbeat slows. And yet, it does not die. It becomes calmer, a kind of cosmic meditation. To stand on this surface, if one could exist there for a moment, would be to witness all of physics at once. Gravity, quantum mechanics, electromagnetism, nuclear force, all four fundamental interactions converging in one equation, too complex to solve, but too perfect to ignore. The airless horizon glows faintly with synchrotron light. The crust hums with vibrations smaller than atoms. Every quiver, every photon, every field line is the echo of balance achieved through unimaginable violence. It is easy to think of neutron stars as ruins, remnants of collapse. But seen another way, they are foundations. Where ordinary matter breaks, they continue. Where other stars burn out, they become timekeepers. Their surfaces are not tombstones. They are thresholds between the known and the almost impossible. As you drift above this world, the sense of perspective shifts. You begin to understand that this surface, only meters thick, carries stories that could define the fate of galaxies. The strength of its crust determines whether mountains can form, and whether those mountains can produce the ripples in space-time we call gravitational waves. Its conductivity governs how long a magnetic field can last, how many millions of years before it fades. Its thermal properties decide how a neutron star cools, how quickly it becomes dark, and what kind of light it leaves behind. In that sense, this thin, silent boundary holds the keys to cosmic evolution. If you close your eyes, if such a thing were possible, you would feel a vibration, a hum that isn't sound but structure. That hum is pressure made musical. Every layer of the surface resonates in harmony with the next. It is the sound of the universe holding itself together. There is no wind, no motion, only symmetry. And yet, that symmetry sings. The journey across the surface of a neutron star is not a walk through terrain, but through laws. Every step is a new regime of physics, every glance a new dimension of density. And with each passing moment, you realize that even in the smallest corner of the cosmos, there exists an order so complete it feels like serenity. This serenity is not peace in the human sense, it is equilibrium. The balance between collapse and creation, the rest state of the universe's most exhausted heart. And so, as we linger at this surface, this skin of light and density, we are reminded that even in endings, there can be grace. The fire is gone, but the glow remains. The chaos has passed, but the pattern endures. To gaze upon it is to understand. Sometimes, stillness is just motion slowed to perfection. And beneath that stillness, deeper layers await waiting to reveal what happens when matter forgets its shape and begins to flow like dough made of stars. Our descent continues. But for now, we rest at the surface, the calm before the spiral. Beneath the calm shell of the neutron star, light begins to fade. The thin crust that gleamed like frozen moonlight now yields to shadow, and the descent becomes a quiet fall into pressure itself. Nothing moves here in the human sense, no wind, no tremor, no echo. And yet, everything is in motion, in the invisible choreography of particles, crushed past imagination. What we are about to enter is neither solid nor liquid. It is a region that disobeys every textbook, a borderland between what matter was and what it might become. The scientists call it the inner crust. I prefer another name, the kitchen of gravity. Here, gravity is not an abstract pull. It is a chef patient, relentless and exact. For millions of years, it has kneaded the remnants of a dead star into shapes that could not exist anywhere else in the cosmos. It does not rush, it does not err. It simply presses until resistance itself becomes architecture. Each meter downward multiplies the pressure by 1,000. And with each step, the familiar world disappears. Atoms, once proud little solar systems of electrons orbiting protons, begin to collapse inward. The empty space that once made them so vast vanishes, squeezed out like air from dough. By the time we've fallen a few meters, even the idea of an atom has ended. The crustal lattice of neutron-rich nuclei starts to deform. Electrons, stripped of their individuality, drift freely through the gaps, a shimmering ocean of quantum electricity. Neutrons leak from the overcrowded nuclei, forming a thin fog that seeps between them. Pressure builds, space shrinks, and matter begins to remember the shape of the forces that created it. Two rivals dominate this subterranean world. The first is the strong nuclear force, a fierce embrace that binds protons and neutrons together. It is powerful, but impatient. Its reach is short, no farther than the width of a single nucleon. The second is the Coulomb force, the ancient repulsion of light charges. Protons push one another away, their positive charges unwilling to coexist. Up above, these forces rarely meet. Space gives them room to avoid each other. But here, under gravity's thumb, there is no room left. The strong force and the Coulomb force collide in perpetual argument. One tries to unite, the other to divide. The result is neither victory nor defeat. It is frustration, a physical tension so perfect that the universe decides to resolve it through geometry. At first, the shapes that emerge are simple. Clusters of protons and neutrons, compact, spherical like pearls in a sea of electrons. Physicists, with a wink of humor, call this the gnocchi phase. Each dumpling floats in the neutron fog, bound together by nuclear glue. They drift, not through air, but through a quantum ocean dense enough to crush the concept of emptiness. If one could somehow illuminate this region, it would not look chaotic. It would shimmer, a glittering suspension of glowing specks, each one a tiny fortress of pressure holding its ground against collapse. But gravity keeps pressing, and pearls are inefficient. They waste space. So the gnocchi stretch. The round clumps elongate, merging into filaments that snake through the neutron sea. Strings of matter weave across the darkness, twisting and looping like pasta stirred by invisible hands. This is the spaghetti phase. Long nuclear fibers, kilometers in length, only meters apart, carrying density like tensioned cables in a cosmic suspension bridge. It is the universe's most intricate embroidery, stitched together by the competition between cohesion and repulsion. Each strand hums faintly with vibration, transmitting stresses through the crust like the strings of a galactic harp. Should a starquake strike above, the waves of strain will rush down these filaments, and for a moment, the entire star will resonate, a soundless symphony conducted by gravity. Deeper still, even the noodles tire of their shape. Filaments merge into sheets, the lines between them vanishing as pressure flattens their pride. Welcome to the lasagna phase. Vast layers of nuclear matter spread like cosmic strata, dense, orderly, shimmering with degenerate light. Between them lie thin layers of neutron fluid, silent rivers separating one sheet from the next. Each plate supports the weight of those above, and yet floats upon currents of subatomic motion. It is at once the strongest and most delicate structure in existence, harder than diamond, softer than silk, perfectly balanced between fracture and flow. If we could touch it, though, nothing human could survive. The attempt, our fingertips would meet resistance so absolute that the sensation would never reach the brain. The signal would die before the thought could form. This is matter at its most obedient. Every force, every motion, every particle held exactly where it must be. Nothing wasted, nothing free. But gravity does not stop to admire its work. It continues to press, and the pattern begins to invert. The solid slabs of lasagna sprout holes, tiny voids where the neutron sea forces its way in. At first, the holes are small, like bubbles in cooling glass. Then they stretch into tunnels, curling into loops that spiral downward. Now we have entered the Bucatini phase, the hollow pasta of the cosmos. Here, the roles reverse. The matter becomes the vessel, the emptiness becomes the filling. The tunnels widen, merge, and weave together until the once solid sheets are riddled with passageways, a labyrinth of nuclear stone pierced by caverns of liquid neutron. If light could travel here, it would scatter endlessly, never finding a straight path out. If sound could travel, it would echo forever without finding silence. Finally, near the base of the inner crust, comes the most surreal transformation of all. The tunnels break apart, their walls closing into bubbles of vacuum, adrift in the density of nuclear matter. This is the Swiss cheese phase, a lattice of holes suspended within a sea of near-solid neutron-proton matter. Here, solid and empty have exchanged identities. Matter and void become indistinguishable partners in a dance of balance. No edge is sharp, every boundary is blurred by the weight of coexistence. It is beautiful in a mathematical way, a structure born not of chaos, but of necessity. Each layer below preserves the memory of the one above, like the verses of a song transposed into new keys. Physicists once imagined this chain of shapes, gnocchi, spaghetti, lasagna, bucatini, Swiss cheese, as mere metaphors to simplify theory. But simulations prove them real. On supercomputers, millions of nucleons are set loose within virtual boxes, governed only by the forces that bind and repel them. They are not told what to do. And yet, inevitably, they assemble themselves into pasta. No randomness, no whim. Only mathematics made visible. In each simulation, the same story unfolds. Clumps, threads, sheets, tunnels, bubbles. A procession of geometry as old as the laws themselves. The universe, it seems, prefers rhythm over chaos. The pasta is not fragile. It is the strongest material known, its tensile strength 10 billion times greater than steel. That strength comes not from density, but from connection. A continuous network that distributes stress across countless bonds. When a neutron star flexes, the pasta stretches, but does not shatter. It bends, it yields, it remembers its shape. Only when the strain exceeds the patience of gravity itself do sections snap, releasing quakes that jolt the surface, sending bursts of radiation into the void, and sometimes, if the fracture is deep enough, rippling space-time itself. Each glitch, recorded in a pulsar's heartbeat, may begin right here in a broken strand of nuclear spaghetti. The deeper layers, near the transition to the core, exist under densities approaching 10, 14 grams per cubic centimeter, about the mass of a mountain squeezed into a teaspoon. There, the distinction between individual nuclei collapses entirely. Matter becomes a continuous medium, a soup of neutrons, protons, electrons, and perhaps even quarks and gluons set free from their cages. It is a region we can only imagine. No experiment on Earth can reproduce it. Even our equations begin to tremble, their symbols bending under the same pressure they describe. The pasta ends, and something nameless begins. In this hidden kitchen, heat still flows. The pasta's tangled architecture controls how quickly the star cools, how easily electrons and neutrinos escape. It may even decide how long the star's magnetic field endures. Where the structure is ordered, heat runs freely. Where it is tangled, energy lingers, turning the pasta into a thermal blanket wrapped around the star's heart. Observations of real neutron stars confirm the hint. Some cool quickly, others glow for decades. The difference lies in their crusts, in how gravity chose to cook their matter. There is humility in realizing that what seems whimsical, a dish of noodles at cosmic scale, holds the key to stellar evolution. But that is the nature of the universe. It loves irony. It hides revelation inside humor. And so we give the most serious matter the most playful name. Because, at some level, naming is an act of affection. When we say nuclear pasta, we are really saying we see the pattern, we respect the order, we marvel at the elegance of pressure turned into design. If we drift back and look down upon this invisible kitchen, we would see no light, no color, no fire, only density folding in on itself, like dough rising under infinite weight. Gravity is the baker, the strong force the yeast, the Coulomb force the resistance. Together they work in silence, producing the universe's most impossible recipe. Time passes differently here. The deeper layers shift slowly, perhaps over millennia. When the crust cracks, the pasta rearranges, smoothing its fractures like dough healing itself. It is alive, in a geological sense, a slow metabolism of structure responding to stress. And yet, in this lifeless environment, there is something hauntingly familiar. The same shapes appear elsewhere, in biological membranes, in the folds of cells, in the networks of brain tissue. The same curves, the same tunnels, the same junctions. Across 40 orders of magnitude, from femtometers to microns, nature writes the same geometry. We are built, it seems, from the same grammar that rules collapsing stars. Perhaps this is the real unity of physics, not the equations, but the shapes that endure. The kitchen of gravity is not a place of chaos, but of compromise. It is where the universe learns restraint. Too much attraction, and the star would collapse into a black hole. Too much repulsion, and it would explode apart. Between the two lies balance, a moment of harmony suspended in pressure. And so, this strange lattice of nuclear matter stands as a monument to moderation. Even in extremity, nature prefers proportion. If we could translate the forces here into sound, it would not be a roar, but a hum, a deep, continuous vibration resonating through the crust. Each frequency corresponds to a shape, each shape to a phase. Together they form a chord, the quiet music of balance. In that music, the neutron star dreams. Its heartbeat above, its pasta below, both playing variations on a single theme. That endurance is a kind of elegance. The deeper we go, the closer we come to the limits of comprehension. Equations falter, metaphors multiply. The human mind strains against its own boundaries, trying to picture something that cannot be pictured. Perhaps that is why this region feels sacred. It is the edge of knowability, a reminder that science and wonder are not enemies, but partners in humility. We can model the forces, we can name the phases, but we cannot yet feel what it is to exist at 10 quadrillion grams per cubic centimeter. Only the neutron star knows that secret, and it keeps it well. In the end, the kitchen of gravity is more than a curiosity. It is the workshop where the universe proves that even death can be creative. A star collapses, and out of its ruin comes structure. Chaos compresses, and from its pressure comes order. From gnocchi to spaghetti, from spaghetti to lasagna, from lasagna to Swiss cheese. The phases are more than metaphors. They are steps in a recipe older than time, how to turn destruction into design. And so we drift, deeper into stillness, past the crust of brilliance, into the layered dark where gravity cooks in silence. The fire of fusion has long gone out. But another fire remains, not of heat but of structure, burning steady in the language of form. The neutron star does not shine with light anymore, it shines with organization, a final defiance of entropy. This is the heart of transformation, pressure becoming pattern, collapse becoming creation. The pasta waits below, silent, strong, eternal, the handwriting of gravity, inscribed in matter itself. Far above the hidden kitchen of gravity, the neutron star turns in the dark. What happens inside its crust is unseen, yet not entirely silent. Across the gulf of space, faint signatures travel outward, ripples in light, in magnetism, in space-time itself. They are whispers of the nuclear pasta below, carrying the slow heartbeat of the densest matter known. The universe is not content to keep its secrets buried. Even the most compressed silence eventually finds a voice. One of the most delicate songs it sends is woven into the fabric of space-time. Continuous gravitational waves. These are not the cataclysmic bursts that roar from colliding black holes, but soft, steady vibrations emitted by neutron stars that are ever so slightly imperfect. A perfectly round star would spin in silence, but the pasta crust is far from perfect. Its incredible strength allows it to hold tiny mountains, deformations no higher than a few centimeters, yet massive enough to create measurable asymmetry. As the star rotates hundreds of times per second, that tiny irregularity drags on space-time, producing a hum that would, in theory, never fade. If our detectors were sensitive enough, we would hear it as a pure tone, a cosmic organ pipe resonating through eternity. So far, the detectors on Earth, LIGO, Virgo, CAGRA, have not heard that note, but their silence is instructive. It tells us that those mountains must be even smaller, or that the crust, though strong, yields sooner than expected. Still, simulations suggest that with next-generation instruments like the Einstein telescope, those hums may finally rise above the noise. The nuclear pasta, frozen deep within a star, might soon reveal itself not by light but by sound, the sound of gravity itself, stretched into rhythm. Yet the pasta does not sing only through waves of space-time. It also breathes through heat. When a neutron star is born, its temperature can exceed 1 billion degrees. Over thousands of years, it cools, releasing its stored energy through radiation and neutrino emission. But the rate of that cooling is not smooth. Some stars cool far faster than others. Some seem to linger in warmth for decades longer than theory predicts. The explanation lies in the crust and in the strange glassy disorder of the pasta layer. Its tangled geometry scatters electrons and neutrinos, reducing how efficiently heat can flow from the core to the surface. The result is an insulating shell, a cosmic thermal blanket that slows the star's chill. In transient systems, when neutron stars are intermittently reheated by infalling matter, astronomers have watched this cooling directly. The star MXB 1659-29, for instance, glowed for years after its accretion ended, defying simple models. The likely culprit? A deep pasta layer that traps residual heat. And yet, paradoxically, the same structure can also accelerate cooling under certain conditions. The periodic potential of the pasta may permit direct Urca processes, enabling neutrinos to escape more easily and carry energy away in torrents. Thus, the crust can act as both insulator and exhaust vent, its role changing with temperature, composition, and magnetic field. To watch a neutron star cool is to watch a dialogue between order and disorder, between the smoothness of geometry and the randomness of entropy. Every light curve is a thermal confession, written by gravity's own chef. Sometimes, though, the star's silence breaks violently. Astronomers call these events glitches, sudden jumps in rotation speed that defy the otherwise perfect regularity of pulsars. A pulsar is a lighthouse of time, sweeping radio beams across the cosmos with such precision that even atomic clocks seem clumsy beside it. But then, without warning, it stutters a heartbeat skipped in cosmic rhythm. The cause, many believe, lies once more in the crust, where elastic stresses have been accumulating for centuries. As the star spins down, its shape slowly adjusts to a less oblate form, yet the rigid pasta resists this change, storing tension like a bent bow. When the strain exceeds the material's limit, the crust cracks, snapping into a slightly more spherical shape. The sudden rearrangement alters the star's moment of inertia, making it spin faster. The released energy shakes the crust and may send seismic waves racing through the pasta network. To us, the event lasts milliseconds. To the star, it is a quake that reshapes its entire skeleton. Each glitch is a reminder that even the strongest material in the universe eventually yields. But it also proves that strength matters. Without the extraordinary resilience of nuclear pasta, such stresses could never accumulate at all. The very imperfections that give rise to gravitational waves are the same that, when overburdened, unleash stellar earthquakes. Strength and fragility coexist here like twin notes in a chord. The pasta's influence extends further still into the invisible domain of magnetic evolution. The neutron star's magnetic field, sometimes 1 trillion times stronger than Earth's, threads through its crust like wires through insulation. Over millions of years, those fields decay, twist, and reconnect, driving the gradual metamorphosis of pulsars into quieter remnants. But the rate of that decay depends critically on the electrical resistivity of the crust. Where the pasta is orderly, currents flow easily, preserving the field. Where it is amorphous and tangled, electrons scatter, resistance rises, and the magnetic field dissolves more quickly. Some theorists believe this explains a mysterious observational boundary. No isolated X-ray pulsars have been found with spin periods longer than about 12 seconds. It is as though an invisible limit arrests their slowdown. The idea is simple but profound, that the pasta's irregularity sets a universal clock. When the resistivity grows high enough, the magnetic field can no longer break the star efficiently, and the spin period freezes. The absence of long-period pulsars is therefore not an observational accident, but a signature written by matter itself. In that sense, the strange crust beneath our feet of imagination has shaped an entire population of stars across the galaxy. Each of these phenomena, the gravitational hum, the thermal sigh, the glitching heartbeat, the fading magnetic aura, offers a window into a realm we will never see. Together they form a kind of indirect astronomy, a science of inference. We cannot visit a neutron star. We cannot hold its pasta in our hands. But we can listen, measure, and model. Every detection, every silence, every curve of light and frequency constrains the unseen physics below. This is the art of cosmic deduction, learning the intimate details of matter through the shadows it casts on observation. It is reminiscent of early geology, when people inferred the core of the Earth from surface tremors. Except here, the earthquake is measured in microseconds, and the tremor is space-time itself. The paradox of studying nuclear pasta is that we know it only through what it prevents us from seeing. It muffles heat, delays signals, alters rotations, always shaping the observable by withholding it. In that way, it resembles history itself. The deeper the layer, the harder the truth, the slower the revelation. And yet, those delays are precious. They stretch moments of discovery into centuries of curiosity. Even silence becomes informative when the silence comes from a star. When scientists model these processes on supercomputers, they are not just simulating physics. They are conducting archaeology across impossible scales. A single simulation step might correspond to a nanosecond in real time, yet it describes stresses that unfold over millennia. The algorithms track neutrons and protons dancing under conditions that would annihilate any laboratory. The resulting structures, networks of sheets, tunnels, and bubbles, are frozen echoes of cosmic evolution. From those models come measurable predictions: how much energy a glitch can release, how thick the insulating layer must be to match observed cooling, how high a mountain could survive before collapsing. The beauty of the approach is that each of these theoretical quantities corresponds to something we can, in principle, test. If a future gravitational wave detector catches a continuous tone, its amplitude will tell us how rigid the crust is. If an X-ray telescope observes a cooling curve that deviates from prediction, that deviation will reveal how tangled the pasta truly is. The laboratory and the telescope become partners, one forging matter in code, the other verifying it in light. Beyond the measurements lies philosophy. The very fact that we can predict, with some confidence, the behavior of matter at 10 trillion times the density of water is itself an act of faith in the continuity of nature. We assume that the laws of quantum mechanics, tested in fragile atoms on Earth, remain valid when atoms are crushed out of existence. Every successful match between theory and observation, every glitch modeled, every cooling rate explained, is therefore a reaffirmation of unity. It tells us that even at its most alien, the universe still speaks our language. There is also humility in these signals. Each observation we make depends on extraordinary luck. A pulsar aligned just right, a burst timed perfectly, a detector quiet enough to notice. The cosmos offers its hints sparingly. But when it does, it rewards patience. Consider the first detection of gravitational waves in 2015, a century after Einstein's prediction. Those waves came not from a neutron star crust, but from colliding black holes, yet they prove that space-time can sing. The next verse, many believe, will come from the Pastor, a fainter melody, continuous, subtle, but no less profound. The patience required to hear it mirrors the patience of gravity itself, which has been shaping these structures for eons. From a broader view, nuclear pasta is more than a curiosity of condensed matter. It is a bridge between scales, connecting the quantum to the cosmic, the invisible to the observable. The same physics that governs a few femtometers of nuclear interaction decides the rhythm of stars, the evolution of galaxies, and the future of detectable waves. Each observation of a pulsar's timing or an X-ray afterglow is thus a measurement not only of astronomy, but of nuclear physics. The star becomes an instrument, the universe its laboratory. And we, listening across the void, are the scientists who learn by echo. In this realization lies a quiet kind of spirituality. To study these signals is to engage in empathy with the inhuman. We imagine what it feels like to be matter under crushing pressure, to vibrate as gravity molds you into impossible shapes. We translate suffering into structure, strain into signal. The more precisely we measure, the more deeply we understand how resilience is written into the very fabric of existence. Perhaps that is why these studies, though abstract, often move people emotionally. They reveal that endurance is not a human invention but a cosmic principle. As technology advances, our ears will sharpen. Future observatories, the Einstein Telescope, Cosmic Explorer, Athena, Lynx, will probe frequencies and wavelengths that today lie beyond reach. They may finally catch the hum of a spinning pasta crust, the flicker of a cooling curve reshaped by tangled geometry, the aftershock of a magnetic quake. When that happens, we will have confirmed not just a theory, but an aesthetic, that the universe, even in collapse, composes beauty. And when the data arrive, they will not merely add to catalogues. They will refine our sense of belonging. Every gravitational wave detected, every pulsar mapped, narrows the distance between imagination and reality. We will know, more precisely than ever, how thick a star's crust is, how strong its matter, how swiftly it ages. But more than that, we will know that somewhere, beyond light's reach, the quiet labor of gravity continues, baking, shaping, balancing. The kitchen of gravity never closes. Its products, the waves, the pulses, the fading fields, travel outward as gifts. They cross the vacuum and touch our instruments, whispering stories of pressure and time. And as we decode those stories, we become participants in a cosmic conversation billions of years long. The pasta may remain hidden, but its consequences illuminate the night sky. In the end, the signs we can see are less about spectacle and more about continuity. They tell us that every effect has a cause, every silence a source. A pulsar's glitch, a star's gradual cooling, a magnetic field's decay, all are expressions of the same underlying dialogue between gravity and the strong nuclear force. The interplay that carved patterns in the crust continues to shape the observable universe. Through those signs, we trace the outline of something eternal, the persistence of order amid decay. The neutron star, turning still in its dark orbit, embodies that persistence. Its light may fade, its field may weaken, but the rhythm remains. Beneath its surface, the pasta endures flexing, cracking, healing, whispering through space in the language of phenomena we call science. To understand those whispers is to hear the universe breathing, and to listen well is, perhaps, the closest we come to peace. To understand a world we can never touch, we build another one inside machines. In laboratories that hum through the night, the universe is reborn in silicon particle by particle, equation by equation, until the unimaginable becomes calculable. This is the realm of simulation, the bridge between observation and intuition, between the unreachable star and the human mind that insists on reaching it. For the study of nuclear pasta, it is not a luxury, but a necessity. No experiment on Earth can reproduce the crushing densities or the tidal forces inside a neutron star's crust. The only way forward is through imitation, a reality translated into numbers, then unfolded on screens as if the computer itself were a miniature cosmos. Every simulation begins with a paradox. We want to model simplicity, but the simplest questions, what shape does matter, take under such pressure, how does it break, how does it heal, require unthinkable complexity to answer. Physicists respond to this with a kind of artistry. They reduce the chaos of the cosmos into a set of rules so pure that even a supercomputer can obey them. Within these digital universes, every nucleon is a point in space, bound by the same forces that rule the real one. The strong nuclear embrace that binds, the Coulomb repulsion that divides, the gravitational pull that anchors everything in context. Then they press run, and the invisible begins to move. The most familiar of these techniques is molecular dynamics, though the molecules in question have long since vanished. Here, the building blocks are not atoms, but nucleons, protons, and neutrons treated as individual particles, interacting through phenomenological potentials, simplified echoes of the true nuclear force. The code follows Newton's equations, time-stepping through billions of femtoseconds, watching how clusters merge, stretch, or dissolve under immense compression. Because each nucleon must interact with all the others, the number of calculations grows faster than the imagination can follow. A single run may involve hundreds of thousands of particles and consume millions of CPU hours. Yet what emerges from this digital pressure cooker is astonishingly lifelike. Dumplings form, strings stretch, sheets flatten, tunnels appear. Out of pure mathematics arise the same shapes we have inferred from theory gnocchi, spaghetti, lasagna, proving that the universe's recipes can be reproduced in code. But the beauty of molecular dynamics lies not only in what it creates, but in what it reveals about our limitations. The simulations often assume a proton fraction far higher than that of real neutron star crusts, simply because otherwise the equations become unstable. They treat quantum effects like the indistinguishability of particles, or the whisper of superfluidity as optional, replaced by classical analogues. Time and size are finite. A few thousand femtometers of matter must stand in for a region that, in reality, extends for kilometers. To bridge that gap, scientists employ periodic boundary conditions, looping the edges of their computational box so that matter exiting one side re-enters from the other. The result is a repeating universe, infinite by illusion. Yet even within that constraint, the patterns hold. Geometry seems to care little about context. Whether in a box or a star, it organizes itself with the same stubborn grace. Beyond the molecular dynamics approach lies a more intricate and expensive method, the quantum mean field family, represented by calculations such as Skyme-Hartree-Fock. Here, each nucleon is not a dot but a wave, a probability cloud shaped by the Pauli exclusion principle and the dance of spin-orbit coupling. The equations no longer follow individual trajectories, but evolve fields, densities, potentials, currents across a discretized grid of space. These simulations are far smaller, often confined to a single unit cell of matter, but they reach deeper into the quantum heart of the problem. They reveal how the energy of the system changes with curvature, with density, with the subtle tug of symmetry energy that determines how neutrons and protons coexist. In these models, the transition from gnocchi to spaghetti to lasagna is not a visual metaphor, but a precise shift in the balance of forces. The computer does not know the word pasta, yet it discovers it anyway. Other methods experiment with treating the pasta not as a collection of particles, but as a fluid of fields. The lattice-Boltzmann approach, for instance, translates the motion of nucleons into flows of density and momentum, allowing researchers to explore how these structures deform and relax under stress. Meanwhile, hybrid frameworks such as MADNESS, an adaptive multi-resolution solver, break the problem into hierarchies of precision, focusing computational power where it matters most. Each technique trades one form of imperfection for another: size for detail, speed for accuracy, simplicity for realism. The frontier of the field is not a single equation, but a negotiation among them, an evolving consensus on how best to capture the invisible. Computation, for all its elegance, is never free. To simulate a patch of crust no larger than a dust grain, scientists must command some of the most powerful machines ever built. Rows of processors churn through the night, their fans whispering like the cosmic wind they attempt to imitate. Petabytes of data flow through cables like rivers of virtual matter. And when the run finally ends, the scientists are left not with a star, but with numbers, columns of positions, velocities, energies. Only through careful analysis do those numbers reveal the hidden architecture, networks of tunnels, plates and bubbles, each corresponding to a phase in the celestial recipe. The process feels less like discovery than translation, turning the silent logic of the universe into a language that the human eye can recognize. The limitations of these models are both technical and philosophical. On the technical side, they struggle with scale. The structures within a neutron star's crust can extend for kilometers, yet our simulations rarely exceed a fraction of a millimeter. The boundary between micro and macro must therefore be inferred rather than seen. Finite size effects, artifacts of confinement, can distort results, introducing spurious periodicities or suppressing long-range correlations. To mitigate this, physicists employ twisted averaged boundary conditions, cycling through multiple configurations and averaging them until the artificial symmetries cancel out. Even then, uncertainty lingers. The computed shear modulus of pasta may vary by an order of magnitude depending on the choice of potential or proton fraction. The lesson is humbling. In a realm where no experiment can verify, precision becomes an act of faith. The philosophical limitation cuts deeper. A simulation, however detailed, is still a metaphor, an arrangement of symbols pretending to be substance. We speak of running the universe, but what we truly run are our assumptions. The code is a mirror, polished by intellect, reflecting both the cosmos and our methods of perceiving it. When it succeeds, it is because the universe itself obeys a kind of mathematical compassion, allowing simple forms to stand in for its vast complexity. When it fails, the error reminds us that reality is richer than any model. The nuclear pasta, with its wild topologies and shifting symmetries, constantly tests the boundaries of this metaphor. It behaves like a living system, generating self-organized patterns from competing constraints. In doing so, it blurs the line between physics and philosophy, between prediction and imagination. Yet despite these hurdles, progress continues with almost biological persistence. Each new generation of supercomputers extends the frontier by a few orders of magnitude. Simulations that once required months now complete in weeks. Visualizations once crude now resemble art. Machine learning has entered the stage, sifting through oceans of data to identify recurring motifs, mapping out a multi-dimensional phase diagram that charts where each form of pasta prefers to live. Neural networks, trained on thousands of configurations, can now predict transitions between shapes with uncanny accuracy, discovering hidden sweet spots of density and temperature. What was once guessed by intuition is now illuminated by pattern recognition. The machines, in their quiet way, have learned to dream of stars. Recent work goes even further, merging computation with theory into hybrid frameworks that capture quantum superfluidity and magnetism, long absent from classical models. In these simulations, neutrons glide through the lattice like paired dancers, their motion frictionless, yet synchronized with the magnetic field that threads the crust. The presence of a strong field up to 10 to the power of 18 Gauss in magnetars distorts the shapes of the pasta, elongating filaments and aligning sheets as if the star itself were combing its interior into order. The inclusion of such effects has begun to explain phenomena once mysterious: why certain pulsars emit bursts of X-rays, why others remain eerily quiet, why some seem to glitch in clusters rather than alone. Each refinement brings the digital star closer to its real counterpart, though the gap between them may never close completely. The cost of these achievements is immense. Simulating a few cubic micrometers of pasta can demand millions of CPU hours and generate terabytes of output. Scientists often describe the experience as both exhilarating and humbling. Exhilarating because each run reveals something unprecedented. Humbling because each revelation immediately raises new uncertainties. The more accurately we model the crust, the more questions arise about the core. The better we understand the microstructure, the less certain we become about its global behavior. Progress in this domain is a spiral approaching truth through cycles of approximation, each turn narrower than the last. Still, there is poetry in that spiral. To compute the behavior of matter at nuclear density is to reenact creation itself. Every simulation, however abstract, is a miniature Big Bang, a universe in a box evolving toward equilibrium. Watching particles self-organize into pasta shapes evokes the same wonder as watching galaxies form. Gravity replaced by the strong force, stars replaced by clusters of nucleons. The scale changes, the melody remains. And through this melody, we hear the deeper truth that structure is the universe's native language. Whether in code or in cosmos, the same logic of tension and compromise governs all. The future of these simulations is as vast as the stars they model. As computing power grows, researchers envision coupling the microphysics of pasta directly into full star simulations, allowing the crust to interact dynamically with the magnetic field and rotational evolution. Such multi-scale models could, for the first time, predict observable phenomena glitches, thermal relaxation, gravitational wave signatures from first principles. Others dream of uniting these digital experiments with machine learning algorithms that continuously adjust parameters based on real-time astronomical data. The result would be a self-updating universe, a feedback loop between observation and computation where each refines the other. In that sense, the line between telescope and supercomputer would blur until both became parts of a single instrument, the collective eye of civilization gazing into its own equations. Even more daring are the connections emerging beyond physics. Biophysicists have noticed that the same shapes appearing in nuclear pasta sheets, tunnels, gyroids, also arise in cellular structures, such as the endoplasmic reticulum. Across 40 orders of magnitude, matter seems to reuse the same solutions to geometric frustration. This has inspired cross-disciplinary projects where models of neutron star matter inform studies of membrane folding and vice versa. It is as if the universe, indifferent to context, keeps writing the same poem at every scale. The lesson is profound. Simulation is not imitation but continuation. By modeling the unseeable, we participate in the same creative logic that shaped it. In the end, every simulation is a conversation with the unknown. The computer hums, the scientist waits. Numbers appear, forming constellations across screens. Each frame is a frame of time, a reminder that patience itself is a scientific tool. The invisible world within the star is not conquered by power, but revealed through persistence. We build these digital stars not to replace the real ones, but to remember that understanding is an act of empathy. The attempt to feel what cannot be felt. When the servers finally fall silent and the data rest on drives, the scientists step outside. Above them, the night sky burns with real stars, each one a potential laboratory of matter beyond imagination. Somewhere among them, the pastor layers of countless neutron stars are shifting, cracking, healing, composing their silent symphony. The simulations may never capture every note, but they allow us to join the audience to listen across light years and recognize in those distant vibrations a reflection of our own curiosity. And so the work continues. We compute because we cannot reach. We simulate because imagination is the only vessel sturdy enough to cross the gulf. Every algorithm, every visualization, every line of code is a small act of faith that the universe is intelligible. In that, faith lies the bridge between thought and matter, between question and star. The invisible simulations, humming quietly in the background of human history, are our most intimate observatories. They remind us that to model the unthinkable is, in its own way, to touch it. The story of nuclear pasta is not finished. Like the layers within the star itself, our understanding is still unfolding, sheet by sheet, filament by filament, towards something deeper, something more complete. Every discovery that seemed to close a question has instead opened another, revealing that what we once called structure may only be the beginning of a greater architecture of matter. If the earlier chapters of this exploration were written by theory and simulation, the next will be written by synthesis, the union of physics, computation, and imagination, all converging on the same question: what is matter, really? When pushed to the edge of existence, the first horizon lies in refinement. The models we have today, molecular dynamics, mean field frameworks, Boltzmann lattices, are extraordinary but still incomplete. They describe a frozen picture of matter, where neutrons and protons behave as obedient marbles, sliding through predictable potentials. Yet the real crust of a neutron star is not static. It trembles with superfluid flows, vibrates with magnetic tension, and fractures in silence under unimaginable strain. To capture that reality, simulations must learn to breathe. Researchers are building hybrid codes that marry quantum superfluidity with magnetoelastic dynamics, allowing neutrons to move as paired condensates that glide frictionlessly through the lattice of pasta. When a magnetic field threads such a medium, it does more than pull, it organizes, aligning filaments like iron filings around a cosmic magnet. These effects will redefine not only the pasta's geometry, but its observable fingerprints, the way it stores stress, the way it cools, even the way it sings through gravitational waves. To bring such complexity to life demands computational power that only the newest generation of exascale machines can offer. In laboratories from Los Alamos to Riken, researchers now run digital stars containing tens of millions of nucleons, their virtual crusts pulsing in time with equations that have never before been solved at such scale. But brute force alone is not enough. The field is entering the age of machine learning, where algorithms trained on thousands of simulations learn to recognize hidden order within apparent chaos. Neural networks can already distinguish between gnocchi, spaghetti, lasagna, and their inverted cousins with superhuman accuracy, mapping where each phase prefers to exist in the three-dimensional landscape of density, temperature, and proton fraction. They see transitions not as abrupt steps but as smooth continuums, discovering gray zones where multiple forms coexist, a digital echo of the amorphous, glassy reality inside real stars. From this deluge of data, a new principle has begun to emerge: universality. Despite vast differences in conditions, every simulation shows that the transition from one pasta shape to another occurs when the filling factor, the fraction of space occupied by nuclear clusters, reaches a narrow, almost constant threshold. Around 30 to 40% of the available volume, geometry rebels against itself, and matter reorganizes to relieve frustration. This simple rule seems to hold regardless of the details of the nuclear force or the choice of equation of state. In 2025, several teams proposed that this universality arises from curvature corrections in the liquid drop model of nuclear matter, suggesting that surface energy rather than density alone dictates the dance of shapes. If confirmed, this insight could transform how we model not only neutron stars, but all dense nuclear systems, from collapsing supernova cores to heavy ion collisions on Earth. The filling factor, humble and abstract, might be the Rosetta Stone of strong force geometry. Yet the future of nuclear pasta research will not remain confined to code. It will unfold in the skies through multi-messenger astronomy, where light, neutrinos, and gravitational waves converge into a single narrative. The detection of the binary neutron star merger, GW170817, proved that space-time itself can carry whispers from these extreme interiors. The next generation of detectors, the Einstein telescope in Europe, the Cosmic Explorer in America, will be sensitive enough to hear continuous gravitational waves from solitary neutron stars. Their amplitude, frequency, and decay will depend intimately on the rigidity of the crust and the pattern of pasta beneath it. In those signals, we may one day read the texture of matter itself, how it cracks, how it flows, how it holds the memory of a dying star. For the first time, the equations of nuclear physics could be tested not in accelerators, but across light years, by listening to the heartbeat of the universe. Meanwhile, other astronomers are looking toward the quiet signatures of cooling the slow fading of accreting neutron stars once their external heat sources shut off. Observations of systems like MXB 1659-29 have already shown that these stars cool more slowly than theory predicts, as if wrapped in an insulating blanket. The culprit may well be the glassy, disordered structure of nuclear pasta, scattering electrons and trapping heat deep within. Paradoxically, the same disorder that lowers thermal conductivity could also enable faster neutrino emission through direct Urca processes, creating a push and pull between insulation and release. Future space telescopes will trace these thermal curves with exquisite precision, allowing astrophysicists to reconstruct the microphysics of a crust they will never touch. Each temperature drop will be a clue, each plateau a signature of pasta frozen in place. And then there are the magnetars, those unruly stars with magnetic fields, 1,000 times stronger than ordinary neutron stars. Within their crusts, magnetic tension twists the nuclear pasta into new configurations, storing stress that can erupt as X-ray flares or gamma-ray bursts. Recent simulations suggest that such fields can alter the very topology of the pasta, favoring aligned filaments and connected networks. When those networks fail, the energy released could match that of the brightest flares ever recorded. By comparing flare frequencies, durations, and spectral fingerprints, scientists hope to deduce the mechanical laws governing pasta at 10 to the power of 18 Gauss. In a sense, every burst of light from a magnetar might be a crack echoing through a cosmic lasagna sheet, resonating across the galaxy. Another frontier lies in the aftermath of destruction, the moment when neutron stars collide and eject fragments of their crust into space. These shards, once part of the pasta layer, are shredded into the material that seeds the universe with heavy elements through the R process. Whether the unique composition of the pasta influences this nucleosynthesis remains an open question. Does the geometry of the crust determine the abundance of gold, platinum, and uranium scattered into space? Does the disintegration of a lasagna sheet leave chemical fingerprints in the debris clouds we observe? Future high-resolution spectra from kilanovae may reveal whether the universe's most precious metals carry within them the memory of nuclear pasta torn apart. While astrophysicists peer outward, theorists look inward toward the core of computation itself. Exascale machines now allow for coupled simulations that integrate nuclear microphysics directly into stellar dynamics. Instead of treating the crust as a rigid boundary condition, These new models let it evolve, crack, melt, reform in response to spin-down, accretion, or magnetic stress. The result is not a static map, but a living star, capable of producing realistic glitch patterns and heat transport profiles. Some groups even envision a global PASTA database, where thousands of simulated crusts with varying conditions feed directly into astrophysical codes, reducing uncertainties in population studies. The boundaries between nuclear physics, data science, and astronomy are dissolving, replaced by a single shared goal to make the invisible calculable and the calculable observable. Beyond physics, the field is starting to reach across disciplines in unexpected ways. Biophysicists have noticed that the self-assembled shapes of nuclear pasta sheets, tunnels, gyroids, mirror those of cellular organelles, such as the endoplasmic reticulum. Though separated by 40 orders of magnitude in density, both systems arise from the same geometry of frustration, surfaces seeking minimal curvature under conflicting forces. This resemblance is more than aesthetic. By studying one, scientists can understand the other. Computational models of nuclear pasta are now being adapted to study membrane folding, while insights from soft matter physics refine our view of neutron star crusts. The universe, it seems, reuses its best ideas, repeating them from the scale of molecules to that of stars. What we call life and what we call matter may differ less in kind than in context. The next step will be integration, bringing all these threads into a coherent predictive framework. Imagine a virtual neutron star, its layers built from first principles, a magnetic field generated self-consistently, a crust textured with evolving pasta, a core that superflows and interacts dynamically with its surroundings. Such a model would be able to reproduce every observable, from the timing of pulsar glitches to the thermal relaxation after accretion bursts, from the frequency spectrum of gravitational waves to the secular decay of magnetic fields. It would not only explain what we see, but anticipate what we have not yet observed. In this sense, nuclear pasta could become the cornerstone of a unified theory of dense matter, a language through which the cosmos narrates its own interior life. Even as theory advances, humility remains the field's guiding virtue. The more we learn, the more we see the boundaries of our knowledge expanding like an infinite horizon. Nuclear pasta challenges us not merely to compute, but to contemplate, to recognize that the universe's most extreme objects are not violent endpoints, but delicate laboratories of balance. Within those kilometers of compressed matter, attraction and repulsion, order and disorder, rigidity and flow coexist in fragile harmony. The deeper we peer, the more this microcosm resembles ourselves. Systems caught between symmetry and chaos, between endurance and collapse. There is poetry too in the tools we use. Every supercomputer with its humming racks and blinking lights is a monument to the same tension that shapes nuclear pasta, the struggle between coherence and entropy. Each line of code is a thread in a cosmic web connecting human curiosity to stellar matter. The equations that describe neutrons sliding through potential wells are, in a quiet way, equations of empathy. Attempts to imagine what it feels like to be matter under such pressure, to hold together when everything tries to pull you apart. The future of this research, then, is not simply technological or observational, it is existential. By tracing how matter organizes itself under the most extreme conditions, we are, in a sense, studying resilience. The crust of a neutron star endures forces that would obliterate any known material, yet it does not disintegrate. It reorganizes. It transforms frustration into structure, chaos into pattern. Perhaps this is the universe's oldest lesson, that endurance is a form of beauty, that even in the collapse of a giant star, creation continues in another form. One day, perhaps soon, the results of these efforts will arrive not as equations but as images, maps of the unseen, reconstructed from gravitational waves and thermal echoes. They will show that deep inside what was once thought to be lifeless, matter moves with quiet grace. When that day comes, the term nuclear pasta will no longer sound whimsical. It will sound reverent, a reminder that language itself must bend to describe the creativity of nature. Until then, the work continues in silence. Supercomputers hum, telescopes wait, minds wander through the corridors of density and force. Somewhere, a graduate student runs yet another simulation, watching patterns emerge on the screen, lines twisting into sheets, sheets perforating into bubbles. It is a small miracle each time, a glimpse of order born from nothing but equations. And as those patterns stabilize, a realization dawns. We are not just observers of the universe's architecture, we are participants in its unfolding. For in the end, to study nuclear pasta is to look into a mirror. The same principles that shape matter inside a star shape the structures of our thought, the drive to connect, to balance, to create meaning from tension. Gravity gathers atoms into stars. Curiosity gathers minds into science. Both are expressions of the same cosmic instinct, to build coherence from chaos. The neutron star, in all its crushing silence, becomes a metaphor for us, a heart of collapsed brilliance, still beating beneath the weight of its own history. So, the next time you gaze at the night sky and imagine those distant points of light, remember that within some of them, matter is weaving the strongest fabric in existence, one that defies comprehension, yet mirrors the architecture of life itself. And know that somewhere, on Earth, another kind of star glows faintly. A room of computers, a group of scientists, a shared act of imagination. Between them flows the quiet thread that ties understanding to wonder. That thread, invisible yet unbreakable, is the true pasta of the cosmos.